Okay, let me introduce our next speaker, Hosung Kwak from EQS. Hosung Kwak is currently PhD student in Department of Physics at KAIST. He is a lab member of Professor Haung Jung's Complex Systems and Statistical Physics Lab and currently conducting research on the Mpemba effect in non-equilibrium statistical physics. Today he will be presenting a talk titled Two-Qubit Engine Fueled by Entanglement and Local Measurements from the same titled paper. Please join me welcoming today's presentation.
Wow. Hello. My name is Hosung Kwak. Today, I will introduce a paper titled Two-Qubit Engine Fueled by Entanglement and Local Measurement. Oh, okay. Do you guys see my razor pointer? Okay. This is slide on overview of the two-qubit engine proposed by the author. The system consists of two qubit and a daemon. Two qubit and a cute daemon. A daemon creates entanglement, perform a local measurement on one qubit, and extract energy using the information obtained. Now, let's take a closer look at how the engine works. Okay. Now, let me explain how the engine works. There are two qubits A and B, respective transition frequency omega A and omega B, whose evolution is ruled by the Hamiltonian written here. It's written by my hand using good notes. And this is simply a two-level system with different energy level. And before starting the engine, the daemon should be ready for 1-0 state. 1-0 state. 1 is excited, 0 is ground state. Then I believe that who familiar with quantum information theory will understand this setup just by looking. Then engine. The qubit get entangled by coherently exchange on excitation. By adding this term to the Hamiltonian. We call it V, like potential. The original term is H log. LOC log is mean local. The excited or not, and is interaction potential. And this process requires no energy input because it is 0. Because we start 1-0 state and we can calculate the expectation of value, the potential, and initial now it's an energy-free process, no energy cost. And don't be scared by this slide. It is just elementary quantum physics and linear algebra problem. just calculate. And this state evolved as shown here, leading on entangled state. Yes, just entangled state. A and B entangled. We can easily calculate the probability of 0-1 state. By everyone knows the coefficient of here and makes absolute value get probability. It is just linear algebra. And it is step 2. A daemon performs an energy measurement on qubit B at T0. T0 is pi over large omega. Then why T0? Because daemon wants to maximize the probability of 0-1 state. Look at the probability of 0-1 state. It is maximized at T0. Because cosine, yeah. Then that's the state having more energy. Because B here is have more energy. Then next, feedback process. If B is found in excited state, a pi pulse is applied to each qubit. The energy of B is extracted and A is re-excited. Then allowing the demon to gain the energy of Haba delta. Delta is difference. Then, well, demon found B is excited and he looks happy, and pipers applied. Phew! Wow! And in this process, B energy of B is extracted and A is re-excited, and we gain this difference. If not, nothing is done. Look at the face of demon. What a pity. Anyway, the state returned to 1-0 state, and the cycle restart. Both way, and eventually, and the final state is 1-0 state, and we can restart. And check income and outcome. A demon gained energy Haba delta with probability of sine theta square. Sine theta square is just probability for the B when the probability of B is excited. Then the okay. So expected gained energy is Haba delta sine theta square. On the other hand, demo lost average information. Average information is entropy. Before the feedback process, there was uncertainty about whether the system was in 1-0 or 0-1. There uncertainty before check the result. But after the feedback process, this uncertainty disappears. The system is definitely in 1-0 because after the feedback. This means the demon has consumed information about the qubit. We lose this entropy. Then we can define an effective temperature-like quantity tilde T mean as E mean over S mean. And it depends only delta and G because zeta is also defined delta and G here. And a sharp observer might already sense that something unusual is happening here. The first equation of this slide is just the first law of thermodynamics. And there is no internal energy exchange because first the initial state and final states are the same. So there no energy difference is 0. And if we assume isothermal process, temperature is constant, and we can gain this equation. There something is wrong because this is only described by delta and G, and it means also work because we extract from the engine. So, this contrasts with isothermal process, in which energy and entropy inputs are related by the best temperature. In this engine, no. So it can jump over the efficiency of classical engine. We can gain more efficiency than Carnot engine. And wow, look this. It is diverging on the something like it can be diverged. And we can see what happens if this engine operates without utilizing the information. Then the pipers can be blindly applied, even if the state is 1-0 state, still leading to a network extraction. W is Haba delta sine theta square minus cosine theta square because it's when success gain energy, but if we apply pipers when 1-0 state, we lose energy. So W is like that. And there is a problem. If pipers was applied to 1-0 state, then after pipers, the final state is 0, 1 state, but then we can't restart the engine. The initial state should be 1, 0 state. So if you look at the text of the paper, is the it is the text of paper. Note that in all non-ideal cases in which information is not fully consumed, an additional step must be included in the cycle to reset the qubit state. I think the authors are a little irresponsible. It's not good explanation because the reset the qubit states requires more energy or more information. But it is PR paper, so I respect them. They may be smarter than me. Then the authors propose extending this mechanism to a chain of n qubit with increasing frequency. If the daemon successfully transfer the energy throughout n-1 step, then the final excitation reaches the last qubit, effectively achieving energy conversion. In this process, no extraction, just success. Oh, we gain 1, 0 state, 0, 1 state, and repeat. Then now let's find the origin of the measurement pool, because the first law of thermodynamics, the energy should be conserved. Then where the energy we extract where the origin of the energy? Okay, sir. Does the collapse of the wave function cause an increase in energy? No. To answer this, the author introduced a third qubit M, which interacts with qubit B. M represents the measurement device. M is measurement. And I'll give you some details. Before T0, the meter M is prepared in 0 state. Then, do you remember T0? It maximizes the probability of 0, 1 state. 0, 1 state. Then, after T0, we turn on VM, described below here. VM. Just adding this term to Hamiltonian. And just like before, adding this interaction requires no energy because it is 0. And try the calculation, and you can easily find it is 0. And then since chi is much bigger than g, chi is very big, so it is order of g is order of chi. So we can apply perturbation theory. It is very 0, so we diagonalize this and obtain eigenfunction and use perturbation theory. And then after fancy and excited calculation, then we can obtain this result. Then tracing out M, partial trace. Then in this at T0, it is pure state. It became mixed state when Tm. It's just calculation. Then this is equivalent to performing a measurement on B without recording the result. After measurement and don't check the result, then the state would be like this, equivalent to this. The entanglement was break, but we don't. There's some uncertainty in the state, just mixed state. Thus, this process can be interpreted as pre-measurement. So adding VM and waiting until T TM, it is pre-measurement. It's slightly like measurement, but we didn't measured yet. And this is time to reveal what is full. Expectation value of VM decrease while V increase during pre-measurement process. Then VM means interaction energy between qubit B and M, because interaction about B and M. In other words, the interaction energy of the engine and the environment. Engine, AB, qubit AB is engine, and M is environment. So, thus, pre-measurement process is the full. The pre-fairing measurement gives energy to engine. So, it is full. And thank you. so there are something topic I didn't cover in this presentation. Error model work extraction ratio, but I want to enjoy my vacation, so sorry. But if you're interested in these topics, feel free to contact me. I'd be happy to explain them with my fluent native language. Then I think there might be a typo in supplementary material equation 12, but I'm not completely sure. But if you check this, please contact me through KakaoTalk or email or Discord. And might be there is something typo. So, and if you're interested in this paper, read and check, and please contact me. Oh, you're right, or you're full. Thank you. This is real. And anyone question? Oh, yeah.
As long as I understand the kind of advantage from those kind of quantum bit engine when compared to just the ordinary bit and the information engine declared by the other like original ones is coming from the pre-measurement thing. Yeah? A little bit. Like how does this kind of quantum entanglement bit engine gives better can have some potential for exceeding the potential original work efficiency? How could it?
Then you mean the compare with this engine with classical information engine or a classical information?
Sorry, there was a slide that saying that it is kind of better. Yeah. Like how this what's the factor that allows this? It comes from just entanglement or just
The question is that why quantum information engine is better than classical information engine? Is right? 네.
클래시컬한 이걸 리믹보다는 그러니까 클래시컬한 엔진이 그냥 정보 엔진 아니고 그냥 클래시컬한 엔진이
네.
이런 식으로 좀 낫다고 하는데 그게 제가 나중에 뭐 제대로 약간 놓친 걸 수도 있긴 한데 그 이유가 정확하게 뭔가요? 그러니까 이렇게 수식이 기술이라는 건 알겠는데 이렇게 근본적인 이유가 그냥 엔터테인먼트라는 수학의 그런 건지.
그냥 간단. 이것이 그냥 고전적인 엔진보다 더 좋은 효율을 그냥 막 카로노 엔진보다 훨씬 높은 에너지를 쭉쭉 뽑아내고 있는데, 그 이유는 그냥 단순하게 우리가 기존적으로 알고 있던 엔진들은 그 다 연력학적으로 다 평형 그 그냥 열물리학 배울 때 나왔던 그식 하는데, 여기선 사실 베스가 없기 때문에, 베스가 없어서 사실 굳이 말하자면 카르노 열 효율을 따르고 있다고 봐도 됩니다. 왜냐하면 그 고전적 그 열 효율이 1 마이너스 T 고열부 마이너스 저온부인데, 근데 저온부가 0이라고 생각해도 되는, 그래서 효율이 1이다 뭐 이런 식으로 생각할 수도 있는데, 그래서 얘가 약간 그냥 등온 과정을 따르고 있지 않기 때문에 딱히 썰멀 베스와 필요 없는 엔진이라서 이런 효율을 달성할 수 있다. 사실 뭐 사기죠, 뭐. 네. 네.
실제로 같은 경우에 정확한 시간 타이밍이 필요한 것 같은데 시간은 뭐 그 에너지 언설턴티 이런 얘기를 뭐 에러 측면에서 뭐 할 수 있을까요?
이 논문에선 그 그러니까 질문이 나온 게 뭐, 뒤에 에러 모델 뭐 이런 것도 논문에 있는데 뭐 그런 것이 과연 뭐 T0 측정에 대한 언설티나 그런 건 아니고요. 뭐 사실 생각해봤으면 그 양자 쪽 하는 실험 장비 생각해보면 뭐 T0는 정확하게 맞출 수 있을 것 같고 이 정도의 수준의 T0는 여기서 말하는 에러 모델은 우리가 늘 양자 정보 이론 좀 공부하시다 면 자주 나오는 뭐 에러 진짜 에러 커렉션 같은 내용이라서 그냥 에러 커렉션인데 그냥 단순 계산 뭐 거기서 그래서 뭐 미터 M과 큐빅 B의 뭐 뮤추얼 인포메이션 뭐 결국 사실 여기서 드린 게 S인데 S만큼 S를 인포메이션을 소비한데 그게 사실 뮤추얼 인포메이션이다 뭐 그냥 그 정도 얘기고 뭐 하시면 서플리멘터리 읽어보시면 다 있습니다 본문에는 없도록 네,
혹시 그 줌에 질문
네,
괜찮으시죠?
다른 분들도 질문 있으면 뭐 댓글이든지 부탁드립니다.
Thanks for the presentation. Let me applause again to the today's speaker.